All right, well, thanks for the introduction. Okay, so Skip, yes, about myself, I'm a software engineer at Facebook. I worked on Hack, I work on Skip. Very recently, I've switched to FAIR, which stands for Facebook AI Research. And I'm not working on Skip, the compiler itself, but I'm working in Skip, so which is a little bit different, but hopefully I'll have time to go back to the compiler. And so, well, before I say that, yeah, what is Skip? So you can go on the website, skiplang.com. That will give you an overview of the language constructions. And there are really three interesting things about Skip that I'm going to present today. What's really interesting about Skip is that it has a lot in common with React. And that may sound surprising, but one good way of describing it is to say, all right, let's take what's good about React and bake it into a programming language, like where a programming language has been designed from the ground up with the ideas of React. So the ideas of React sounds kind of, general. So I'm going to try to be a little bit specific, right? What's revolutionary about React is that it shifts the way we think about state, right? What you do is you render something as if time was frozen, and then when something changes, it's the job of the runtime of the framework to update things. And the reason why it was so appealing to people is that reasoning about state is horribly hard. That's why you get it wrong all the time when you update something, right? Well, Skip takes the same idea, but makes a full programming language out of it. And you may think to yourself, but why would you do that? Well, there are a lot of things that you can do with it, and that's why I want to show you today. For example, you can build a compiler. Oftentimes, when you're writing code and you use a compiled language, you wish your compiler could just instantly, incrementally compute what's changed instead of, re-going through all the process of building and linking and all that stuff, right? But there are many other things that you can do thanks to it. So before I go further with it, what's the state of the project? So it was a research project that has been going on for like 4 years at Facebook. It's now open source. It's no longer actively developed by Facebook, but it's still developed by me, and I'm going to try to build an open source community around it. Right now, I haven't had time to work very much on the compiler itself. So the compiler is in really good shape. It's pretty stable. But the build system and everything around it needs a lot of polish, and I'd like to work on that before I ask help from the community, because it's unfair to ask people to work on a build system. In the meantime, what I've done is I've built a Docker image with everything installed on it, so that if you want to play with it, you can use this Docker image. In fact, I'm going to use that for my demo today. I'm going to copy-paste that and start showing what the language looks like. I need to make that bigger. I've been told several times that I needed to make that bigger. OK, can everybody see? You first. Is it good? All right, cool. So now let's create a directory for the demo. OK, and we're going to write a first version of a Skip program. That's going to be super simple at first because, you have to start somewhere. OK, so now I have a program. Great. I think everybody has guessed what it does. Great. Now, I want to show you the compiler. So as I said earlier, there are many interesting programs that we could write reactively. And one of them is a compiler. Well, guess what? We've written Skip in Skip. Precisely for that reason. Because what we wanted was a developer experience where you can incrementally, very fast increment on your program. So now the way it works is the compiler is a daemon. And I'm going to talk to that daemon through a client. That client is called SK. So first I do start. And it doesn't work because I haven't created a project. But now I do have a project, which is cool. And then I do sk start. So now I'm telling Skip, you need to attach a daemon to that directory because I'm working on that. And there may be many subdirectories. It might be a large project. Then I say sa check. Says there are no errors. Great, I did a good job. Then I type sk build to say I want you to build that thing. And it says it has written this binary file. So what I could do from there is directly run this binary file, fine. Or I could also go look at the intermediate files that were used, and they're all here. So you can see that there are LLVM bitcode files. It's because we go to native through LLVM. And finally, I can do run. So that's if you don't want to use the binary or copy the binary somewhere. Fine. Of course, most of the time, you want to do all of that in a sequence, right? You don't want to write check, build, da-da-da. It's annoying. So you just type sk, and it's going to do all that sequence for you. And then you keep on typing sk when you want to iterate. OK, now let's go back to my program. And we're going to introduce an error in it. OK, so I run sk check, and the error comes back pretty fast. The interesting thing, so it's good to have errors that come back fast. What's even better is to be able to fix them fast. And error messages in Skip come in multiple parts. So the first part is very classic. It's what every other compiler in the world is going to give you. It tells you invalid return type, which is expected. We have an int. We go to void. OK. The rest, though, is going to point you to the places in the code that you have to modify to make the compiler happy again. So here it's going to say, either you modify this, or you modify this, but the two cannot stay together in the program. So you will have to change one or the other, right? So now if I go back, that is a really cool workflow, right? Because I go to my error, I read it, I say, OK, I understand what's going on, and then it will bring me to what I have to modify, which in this case I will just remove because it's nonsensical. Now I want to show you how this feels like on a much larger program. So in the image, I kept the source code of Skip, which is online and available on GitHub and open source. And I'm going to go into the front end. So the front end of the compiler is all the part that does the checks and static typing and all of that, none of the compilation. If you look at the size of this thing, it's relatively big. We're looking at 50,000 lines of code. The compiler itself is much bigger, but the front end already is a good chunk of code. And I'm going to run a daemon on it, sk start. And so the compiler is also parallel. So it's incremental and parallel. So it uses all the cores to do the type checking. So what you see right now, there are multiple cores running. So now it's ready. And I'm going to open a file. This file defines a data structure that is used in the entire front end. And I'm going to do that on purpose. Now I open this file, and I'm going to introduce an error in something that is used everywhere in the front end on purpose. I'm going to save, and I'm going to check. And what I want you to see is that it came back with 700 lines of errors across multiple files pretty much instantly, which means it rechecked the entire front end in a few milliseconds. Now, if I go back to my original version, save, and go back to check, it came back instantly too. And that is going to be true on very large projects. Like we can scale up to hundreds of thousands of lines of code. You will still get this experience where you can iterate on the code quickly. OK, so that's for the first part of the demo. Sorry about that. Now, how does this work? OK, so at the heart of the language, if there is one thing to know about Skip, is that everything is immutable by default. Now, it doesn't mean that the language is purely functional, like Haskell or others, right? It doesn't mean that you cannot change things. It means that if you want to change something, it has to be explicit. And the compiler will have to know about it, right? Now, what I mean by immutable is very specific, because there are a lot of programming languages with a notion of immutability, but this is not the one we're talking about here. So C++ has const, for example, but it's a much stronger notion of immutability than that. What we mean by immutable is, number one, it's transitive. So if an object is immutable, everything that it points to is immutable too. It includes closures. It includes everything. So if a closure closed over an object, that object has to be immutable too. And also, it's always true throughout time. So there is no way to hold on to a mutable reference. There is no way to turn an immutable object back into a mutable version. OK, so now let me show you what this gives you. Well, before I get into that, the idea, the spirit of the language is to guarantee immutability at the function boundaries. And then within function, we let you have state. We let you program in a way that you're used to. So here I took a very simple example. It's something that builds a vector with the numbers 1, 2, 3. and then adds 1 to every element in that vector. And so I'm going to write that code. So let me go back to my React Europe. And let me write add 1. So I take a vector of int. I go to a vector of int. And then, OK, so one way of doing this is the functional style. So we do v.map x arrow x plus 1. That's fine. That would work. But let's not do that. And let me show you how it would look like with a loop, just so you see what I mean by mutable locally. So let's build a vector called result. And we're going to start off with an empty vector. And then we're going to iterate in v. And we're going to push ELT plus 1, and then return result. So the other thing is that, well, since Christopher was on the team, there's the equivalent of prettier. So when you save, it puts it in a canonical form. And now, so does this work? Oh, I forgot to freeze it. And then you freeze. So the style here is I start with something mutable, I work on it locally, and when I'm ready to cross the function boundary, I freeze it. This operation freeze is going to be optimized away by the compiler, but logically it's a copy. But it's not going to happen at runtime, but logically you can think of it as a copy. Now let's test this with an actual value. And a cool thing that you can use as well is debug. So debug is used to watch anything that is in the program. OK, let's run this. And it seems to work. I've added 1 to every single one of my elements in my vector. Not very interesting up until now. But things are going to become more interesting now that we leverage on the guarantees that come from the language. So remember, I'll show you how to memorize safely and efficiently, parallelize, and use a novel garbage collection scheme. OK, so let's do it together. First, we're going to memorize that function. So a lot of you are familiar with that notion. It basically consists in remembering that you called add1 with a certain value, and next time that you call it around, you will reuse the value instead of recomputing. So in this case, I'm going to use another caller of add1. And I'm going to make it call add1 with the same value v. And here I'm going to call and here I add the keyword memorized, which says you should memorize that code. OK, so now when I run this code, what's going to happen is yes. OK, so I run this code twice. And the interesting part is if I add a little debug here that says that add1 was called. And that should appear only once. OK, because the call was memorized. So the second time I called add1 with the same vector, instead of recalling it, it computed the same thing. And a lot of programming languages let you do that. But here's how it's different in Skip. What happened here during the first call, so this call here, add1, because it's memorized, the vector v was moved to a different heap. And in that heap only lives immutable objects in a normalized form, which means that if two objects are equal, they have the same address in that heap. We call it the shared heap. The same thing happened to the return value of add1. So now, why does this change everything? It changes everything because now during this second call is now extremely cheap. You basically take the pointer v, you look it up in a hash table without comparing the value, because you know that if the value was there, it would have the same pointer. And then you come back with a value that you give back away directly, a pointer. So there was no copy anywhere. Hash table lookup, value came back. Why can I give the value back? Because I know it's immutable. Because the compiler guarantees that you cannot modify that object. Because that's usually what happens with a cache, right? You have a cache, you have to copy objects out of the cache, because usually you cannot prove that the program will not modify the object. But if you can prove it, well, you can hand over a pointer. So now that second call is extremely cheap, and that gives you an idea of how the compiler I showed you earlier actually works. What we do is we memorize strategic points within the compiler so that when something changes, we could reuse intermediate parts very efficiently. Okay, so that's cool. Now, let's look at something else. I'm going to show you how to parallelize this code. So first, let me get rid of my memorization stuff. Okay, so now one notion that you're probably familiar with is async await. An async block is something where you know that it's going to take time or you know that it's going to be blocking. So we actually have that notion in skip too. And so here what I'm doing is I'm creating async blocks, for every element in my array. So of course, in this example, it's not very interesting because this part here is very cheap. But you have to imagine that this part here actually does a lot of work, right? Otherwise, it's not fun. But for the demo, let's assume that there's a lot of work going on here. And then what's going to happen is, well, a lot of things that you're familiar with. We'll have to adjust the code so that it becomes asynchronous. So here, I use the caret to say that it's awaitable. It's just syntactic sugar that means awaitable, because the word awaitable is big. That's what it means. And then I adjust the code to add await. And then I have to come from an asynchronous context. And then the value returned has to be async. And now there are no errors. OK, so now you're probably familiar with that. But what's the difference with the languages that you're used to? The difference here is that all the cores are going to be used. So what happens normally in C#, JavaScript, whatever, right? You have await. What happens is if that value is not ready, we're going to take the current continuation, which is a fancy word for the stack, and we're going to freeze the execution, right? And then there's a scheduler that keeps track of what is available and keeps the core busy, right? So if you make 2 database requests, the first one that comes back, the scheduler is going to give work to your thread, right? Now imagine that same idea applied to n threads. So if 2 database requests come back, well, you can use 2 cores if you have them, right? So why does this work? It works, again, thanks to the language. The language guarantees that you're not sharing mutable state within those blocks. Because that's what unsafe, right? When you have multiple threads, it's fine for them to read data at the same time. The problem is if they try to mutate something, right? But now the language guarantees that's not going to happen. So now you can parallelize things. So now I'm not going to lie to you. You won't be able to write an atomic hash table with it, right? It's not meant to replace system programming. But what's cool about it is that you can write your code in a way that you're very familiar with, async await, and then more or less magically, with minimal effort, it will use multiple core and become multi-threaded, which is really cool. OK, last but not least, garbage collection. So one of the problems that comes back all the time is latency critical software is very difficult to write in a language that is garbage collected, right? And we have that problem with the compiler too. We want the compiler to be fast. And the compiler we're going to use to do all sorts of things like autocomplete, right? I don't want my autocomplete to lag. I want my autocomplete to respond in some amount of time that I can predict, right? And we have that problem all the time. When we use a GC, we basically have to pray the gods of programming that the GC is not going to stop us for too long, right? So the approach that we take in Skip is that there is an overhead that comes from the GC, but that it is predictable. And I'm going to show it to you and show you how it works. OK. So now I'm going to write, I'm going to undo this async stuff that I have. OK, am I good? Yes. So, and I'm going to write a loop, and call the loop is going to call the add1 function. Sorry, my typing is a bit fidgety. To make things a little bit interesting, I'm going to use I and change add1 to add n so that we're not constantly redoing the same work. Unbound variable add1, yes, that is a very good point. No more errors. Okay, and now I'm going to add this construction that you've probably never seen. That's called local GC. Okay, so what does this mean? What this means is you're telling the compiler, I want you to garbage collect code only in that scope. So what that means concretely is that the GC here is only going to look at the memory that was allocated by this loop. At no point in time will it look anywhere else. Why is that so important? It's so important because now you can take this loop, run it in any context, and it will always take the same amount of time. And the memory is going to be clean after it's done. So for example, let's say you have a loop, hypothetical, and your function is called render, right? Well, when you're doing rendering, you often want, 60 frames per second, and you want to make sure that the rendering logic is going to take that amount of time, right? Well, what you do if you're smart is in your rendering logic, you add this local GC call here. And sure, the worst case scenario is that you will have to visit all the memory allocated during that loop. Okay, that could take time, but that's the worst case scenario. And if that's fast enough, then that GC is always only going to take that amount of time. So now, in general, you don't have to worry about these calls because the compiler adds them for you, and if you don't care about performance, you just let the compiler do, right? But if you really care about performance, you have this annotation where you say at no GC. You're telling the compiler, I want to be in charge of where I'm going to pay for garbage collection. And with that, now you can write stuff where latency is critical. You can write a video decoder. You can write a 3D engine. You can write the kind of things that are completely unthinkable to write today in a garbage collected language, right? And the reason why I really wanted that property too is for reactive things to feel smooth, that's something you need. Okay, so in conclusion, there are a lot of things that can be explored with this language skip. If I go back to the 3 things I've presented today, with the built-in caching, so I've showed you memorization. I haven't emphasized very much on the fact that the runtime will keep track of external dependencies for you. So what does it mean concretely? Let's say you're writing a tool that generates code, right? And that tool needs to read a file from, a JSON configuration file, okay? You memorize a bunch of intermediate states because you want the tool to feel incremental, like the compiler I just showed you. Now, it's the job of the runtime to invalidate the caches when the file changes. That's not your job. So now imagine every tool was working this way, because there's so many tools that we're constantly waiting on, right? Possibilities are pretty much endless. The safe parallelism, what I'm excited about is that it makes parallelism accessible to way more people. Right now, it is possible to write all the things I've shown you in C++, and they might actually be more efficient. The problem is the kind of programming it requires is difficult, right? Like acquire semantics, release semantics, those kind of terms are difficult. It's difficult to reason about memory. So what's nice about this model is that it makes it more palatable, right? And finally, about the garbage collection, I'm really excited about the fact that we can write latency critical programs with it. And all of that thanks to Skip. That's it. Thank you. So do we have time?
Okay. Do we have any questions? Okay, we've got a question here. Run over with the microphone.
Thank you very much. Really interesting stuff I've seen. I have a very quick question. Regarding the garbage collector, is there any way to tell, okay, I want to garbage collect only this block, but if through parallelism or maybe this block try to instantiate like random memory, random blocks of memory, is there any way to tell him, but if you need more memory, garbage collect something else?
No. No, no.
Great. That answer gives us more time for other questions. Who else has a question? Put your hand up.
No.
Any other questions? Oh, got one over here.
Okay.
How would you compare this to Rust, for example, which is also looking at similarly sort of worrying about mutable and immutable stuff, but does so by allowing anything to be immutable, but making sure that only one thing has access to the immutable, to the mutable thing at a time, whereas your thing sort of works differently. How would you compare them?
So that's a really good question. So how does this compare to
Can you repeat the
Rust?
question for us?
Yes. So the question was, how does this compare to Rust? Rust has similar ideas behind it, where you can say that things are immutable and you can manage memory in a way that's safe. How does this compare? So Rust is a very different technique. Rust, so first of all, it addresses a different problem, which is a problem of system programming. We're not trying to be a system programming language at all. Now, with that being said, so the way Rust works is it uses unique types, also called linear types, depending on who you call to, or who you talk to. And the idea is, if I can guarantee that there's only one person pointing to that pointer, then it's safe for me to modify that pointer. That's basically the philosophy of Rust, right? And then they've designed an entire type system around that idea. And what they do is they enforce the so-called problem of ownership. So something that was enforced through discipline in C++ has a type system where it will constantly guarantee that when you pass objects around, well, you are either the only owner of that object, or you use a technique called borrowing. I won't get into the details. But what I will say is that the way it compares is that Rust gives you a lot more fine-grained control over how your resources are allocated. But the type system is much more difficult to grasp. Like, it takes time to actually get to be proficient with a borrow checker. The second thing I would add is that the kind of memory model that I've just shown is actually more suitable when your code is very functional. And your code tends to be very functional when you're using a lot of immutable data structure. So let me be very concrete. Let's say I write a service, right? So that service takes in a request, and I process that request. And then I come back with an answer, right? If I write things in Skip, most of the things that I'm going to write are going to be immutable, which means I will allocate a ton of very small objects and have a large memory footprint, right? So now if I take the Skip memory model, this is what's going to happen. I'm going to leak memory, and when I'm done, everything will go away. I'll just hand back the answer and wipe out the memory. If I write it in Rust, I will allocate. When I get to the end, Rust will need to walk all the objects to free them. So that's what I mean by it's less suitable to a very functional style, in the sense that that memory model is more friendly towards functional programming style. Does this answer your question? All right.
Another question.
One last question.
One more. We got one in the front, right over here, Brent.
Hi. So one question. So what about ecosystem? As far as I understand, like this is just a early beginning when you're gonna sort of open source it and build community around it, right?
So it's already open source. The way it happened is that it was a research project within Facebook. Then we open sourced it for people to pick up the pieces. I'm personally keep on working on it, and I hope to build a community in the open source around it. But yeah, I mean, I fully expect it to take 10 years to have a meaningful community. I mean, in a programming language is that kind of timeline, right? I don't expect anybody to go home and start using Skip in production. So, but it's more to present the ideas and to talk to people who are interested in building a community.
And another part of the question, when do you think we can start already try to build something meaningful, production ready? Yeah,
you can use it to build something meaningful, production ready. The problem is more going to be in the risk involved with using a technology that's young. So imagine it has been a team of 10 using this compiler on a daily basis for 4 years, right? And those people are compiler people. So whenever they find a problem, they actually fix it, right? So the compiler is pretty stable, and the code that it generates is very high quality. It's actually very well optimized, and the GC works well. Things work well. But when you have a new technology like that, you have all the problems with the community, right? If the lack of a community means, well, you need a library, right? Well, who's going to write that library? Well, who's going to write the bindings to call the C code, right? Things like that, right? And so I don't want to, try to fool anyone into thinking that this is going to happen overnight. It's not, right? If you are an early adopter who's willing to roll up your sleeves and make this happen with me, then by all means, reach out to me. But if your question is, can I go home, use that in prod at my job? No, right?
Have you tried to use this language inside the company? I mean,
I am not going to talk about that.
all right. Thank you very much.
Thank you.
All right, let's give a big round of applause.
Thank you.
Thank you.
Thank you.